Problem 19 asks us to find numbers a and b so that if x is in the interval from a to 3 or in the interval from 3 to b, that guarantees that the absolute value of x squared minus 2x minus 3 is less than 0.1. And so this is a problem related to limits because I'm interested in this limit as x goes to 3 of the function x squared minus 2x, and which has a value of 3. So if I were to graph my function f of x, y equals x squared minus 2x, then what this is saying is if I let x get close to 3, so here's 3, my y value should be getting close to the value, sorry, that's a 3 as well. Should be getting close to 3. And the inequality that I'm solving says if I consider how far away I am from 3, then I want to know when is my absolute value between negative, or my absolute value less than 0.1, is saying when is my function between 3.1 and 2.9. So let's pick it up from there. The inequality absolute value of x squared minus 2x minus 3 is less than 0.1. Can be replaced by two inequalities. It could be x squared minus 2x minus 3 is less than 0.1, and we also require that x squared minus 2x minus 3 is greater than 0.1. And to connect that to the picture I drew, if I add 3 to the other side, x squared minus 2x, the graph, is less than 3.1, that's the top line, and x squared minus 2x has to be greater than, sorry, that should have been a minus 0.1, is greater than 2.9, and that's the lower line. Well, if I want to solve this, solving it with the number on the right-hand side is actually not useful. So what I really want to solve is I need to subtract the 0.1 to the other side. X squared minus 2x minus 3.1 is less than 0, and x squared minus 2x, and this time I add 0.1, so minus 2.9 is greater than 0. So those are the inequalities I need to solve, and in order to do that, I'm going to use the quadratic formula to find roots and then do sign analysis. Solving this first inequality corresponds to being below the top line. And so I'm really interested in finding these 2 points where the line y equals 3.1 crosses the parabola. And that corresponds to solving one of the quadratic equations. So I need to solve the quadratic equation x squared minus 2x minus 3.1 equals 0, which gives me a solution x equals negative b, that's 2, plus or minus square root b squared is 4, minus 4ac is plus 12.4 all over 2a, so divided by 2. So I get 2 locations where I cross the top threshold, 2 plus or minus the square root of 16.4 divided by 2. Using a calculator, I approximate those values, and the one on the left is negative 1.02485 approximately, and the second is 3.02485. And those are the 2 spots where the graph y equals x squared minus 2x crosses the top threshold. My second threshold corresponds to the equation x squared minus 2x minus 2.9 equals 0. Again, this is a quadratic equation which I can solve using the quadratic formula. X equals negative b plus or minus square root b squared 4 minus 4ac. This time is going to be 11.6, so we add 11.6 all over 2a, and again I can use a calculator to find those values, which gives me x approximately negative 0.97484, or the second is x is approximately 2.97484, I guess. And of those, see, I get two little regions here, one near 3 and another near some other point. We're interested in describing the interval around 3. So the intervals that we find around 3, if I did exact arithmetic, we have 2 plus the square root of 15.6, 2 plus the square root of 15.6 over 2 up to 3, and going on the right, 3 to 2 plus the square root of 16.4 over 2. And so my value A and my values B are these two formulas that we found using the quadratic formula. Problem 20 is again based on the idea of a limit. The limit of my function as x approaches 3 has a value of 7, and we're focused on the definition here. We want to ask, when am I within epsilon of my limit? So we're looking at this approximation error, and it's similar to the previous problem in that I'm solving an inequality, but it's easier this time because I don't have the quadratic formula. So if I start with the inequality absolute value f of x minus 7 is less than epsilon, and I replace it with my formula was 2x plus 1, subtract 7, is less than epsilon. I have a new inequality that's the same as the first, which when I do algebra I get 2x minus 6 is less than epsilon. Now when I'm solving an inequality with absolute values, it becomes two different inequalities without absolute value. So it becomes the inequality 2x minus 6 is less than epsilon, and that's the key conjunction I need, 2x minus 6 is greater than negative epsilon. So now if I solve for x in each of these inequalities, I add 6, 2x is less than 6 plus epsilon, and 2x is greater than, if I add 6, 6 minus epsilon. I now solve for x by dividing by 2. I get x is less than 6 plus epsilon divided by 2, and x is greater than 6 minus epsilon divided by 2. If I distribute that division, I get x is less than 6 over 2 is 3, plus a half of epsilon. And similarly, x is greater than 6 divided by 2, again gives me 3, minus epsilon divided by 2. So on a number line, I've got my number 3, and what I found is that I'm within epsilon in my approximation as long as my x is between 3 minus epsilon over 2 and 3 plus epsilon over 2. And so my solution set is the interval of all things in between. Solution set to the problem, when is my error of approximation less than epsilon. And what I want to point out is that I actually have an interval to the left, so 3 minus epsilon over 2 to 3, and I have an interval to the right, 3 to 3 plus epsilon over 2, and this interval, these two intervals, exist for any epsilon. This gives me the conclusion I was looking for. For any epsilon greater than 0, for any approximation error that I choose, the intervals 3 minus epsilon over 2 to 3 and 3 to 3 plus epsilon over 2 are guaranteed to be in the solution set of my approximation error inequality. For problem 21, we're given a function. It's defined as a piecewise function. I have different rules for I have different tests for the input and different functions, and I want to know, is my function continuous and is it differentiable at each of 3 points. Notice that the first point, -2, is not one of my breakpoints. My breakpoints are -1 and 1. When dealing with a point that's not a breakpoint, I can imagine that this first piece can actually be imagined as breaking into 3 parts. That I use the formula 2x plus 3 in each of the following 3 possibilities. If x is less than -2, if x equals -2, or if -2 and is less than x, but I'm still less than -1. So if you want to think about it in the context of piecewise functions, you can't introduce another breakpoint. You just have the same formula for all of the cases. So let's now test. Is the function continuous at -2? Well, continuity requires that I look at the limits from the left and from the right. Sorry, that's a -2. Let's make that look right. X approaches -2 from the left. The limit as x approaches -2 from the right. Now, because -2 was not an original breakpoint, the formula for my function is the same. It's 2x plus 3 in both cases, whether I approach from the left or whether I approach from the right. Because it's the same formula, I can combine these. All I'm really doing is finding a standard limit, x approaches -2, of 2x plus 3. The sides are the same. And so I get a value, -2 times 2 is -4, plus 3 gives me a limit of -1. If I calculate the value of the function at -2, well, that also uses the same formula. 2 times -2 plus 3 gives me -1. Because the limit and the function agree, I am, in fact, continuous. The second step is to determine if it's differentiable. And to do that, I need to see if the derivatives on the left and the right go to the same formula. So, my derivative to the left, 2x plus 3 has a derivative of 2 when x is less than -2. When x is between -2 and -1, again the formula is 2. And so we're now interested what happens at -2. Well, because the limit of my derivative as x approaches -2 from the left equals 2, and the limit of my derivative function as x approaches -2 from the right also equals 2, and those are the same. These are the same. This implies that f prime at -2 must be 2. And that's only because I was also continuous. If If I'm not continuous, that's not true. And so that allows me to fill in the gap. The derivative is actually 2 at the point, and so I am also differentiable. So now let's look at the other points. At x equals -1, as I'm checking continuity, I need to compare the limit on the left. X approaches -1 from the left of my function. We'll use the formula 2x plus 3. If I come from the right, my function uses the formula x squared. So in the first case, I get 2 times -1, -2 plus 3, gives me a value of 1. And if I plug -1 into x squared, I get the value of 1. And so that tells me that the limits agree, and I also need to find the value of my function. So the limits agree. That tells me that I can do a limit without regard to side. There's no formula involved because they agree the value is 1. If I plug in -1 as an input, then the rule is the second rule, so I use x, the input squared, -1 squared, which is also equal 1. And since these agree, I know that f is continuous. Again, once I know that I'm continuous, I can look at my derivative. We know that the formula uses the formula 2 if x is less than -1. It uses the formula 2x if I'm between -1 and 1, but I don't know what happens when x equals -1. So I need to check my limits. If I take a limit as x approaches -1 from the left of the derivative, I get 2. If I approach the limit as x approaches -1 from the right for my derivative function, I need to take the limit of 2x as x approaches -1, which gives me -2. Because these are different, this will be f prime from the left at -1. This is f prime from the right at -1. We know f prime from the left does not equal f prime from the right. And so we're not differentiable. We are continuous, but not differentiable. And so there is no value of the derivative at -1. The third case asks us to consider what happens at 1. So we do the same thing. If I take the limit as x approaches 1 from the left, and I find the limit of my function as x approaches 1 from the right, coming from the left, I use the x squared formula. Coming from the right, I use the 2x minus 1 formula. And so from the left I get a limit of 1. From the right I get a limit of 1. Because these agree, I know that the limit of my function as x goes to 1 doesn't depend on the side and has a value of 1. If I look at f of 1, the input of 1, I go back to my rules. X equals 1 uses the second rule. And so I get 1 squared equals 1. Because the limit of a function as x approaches 1 equals f of 1, f is continuous at 1. So then we turn our attention to differentiability. Again, we think of our derivative in a piecewise formula. We know that it uses the formula 2x when I'm between -1 and 1. And I use the value 2 when x is greater than 1. But we don't know what happens when x equals 1. We leave that empty. When I now calculate the derivative from the left and the derivative from the right, I can use the limit as x approaches 1 from the left of my derivative formula. And this only works when it's continuous, which is our case. So coming from the left, I'm using the formula 2x. And when you plug 1 in, you get the number 2. Coming from the right, my derivative formula is simply the number 2. And that's the value of 2. Because these agree, the slope coming from the left matches the slope coming from the right. We know that the slope at 1 is equal to 2, and my function is differentiable. F is differentiable at 1. Problem 22 gives us a piecewise function and asks us to use the definition of the derivative to determine if f is differentiable at 2. For this problem, we need to know the definition of the derivative. The derivative at 2 is the limit as h goes to 0 of the formula f of 2 plus h minus f of 2, which gives me a rise, divided by h, which gives me a run. Now, because I have a piecewise formula, I need to deal with this limit from the left and the right, and I need to do it separately. And so I put down the definition. It's the same definition. The only difference is whether I approach from the left or the right. Now, when I approach from the left, the value of the function f of 2 plus h needs to use the formula that comes from the left. When I come from the right, when h is greater than 0, I need to use the formula corresponding to being to the right of x equals 2. Now, f of 2 always uses the second rule. So let's just be careful about that. It's 3 times 2 minus 2, which is 6 minus 2 is 4. Okay, so when I come from the left, I'm taking a limit as h goes to 0 from the left, and the formula that I'll use is the square of the input. So we'll take 2 plus h and we'll square it. We subtract f of 2, which we found was 4, and we'll divide that by h and take the limit. Let's set up the second one as well. We're taking the limit as h approaches 0 from the positive side. And on the positive side, our formula is 3 times the input minus 2. So 3 times the input minus 2 is the value of the function. We'll subtract 4, that's the value of the function at 2, and then we'll divide by h. Okay, so now it's algebra. I need to expand 2 plus h squared, and I'll need to distribute the 3. So I expand those terms, and now we simplify. In the first limit, the 4's cancel. In the second limit, 6, and then subtracting 2, subtracting 4, those cancel. So when I simplify this, I get the limit h is now a common factor. H times 4 plus h over h. Those h's now cancel away, and the limit that I get as h goes to 0 is the limit of 4 plus h gives me a value 4 plus 0. When I calculate the limit on the right, notice again I have a limit of 3h over h. My h's cancel. As h goes to 0, I just am left with the value 3. And notice what we found. The derivative when calculated from the left gave me 4. The derivative when calculated from the right gives me 3. These are not equal. So my function is not differentiable.